You should have been informed right now by Zoom that this webinar is being recorded. We ask you to please follow the general webinar courtesy rules, to please mute your microphone if you're not speaking, and the presenters will give you the floor as needed. And lastly, for the Q&A session, we ask that you enter your questions for the presenters through Slido. You can access Slido through the QR code or on the link that we will share now in the chat. And if you scan the QR code, you will actually right now be able to see one of the questions. So through Slido, you can ask your questions for the Q&A session, but at the same time, we will be posting throughout the webinar some questions for you, the audience. We want to make this webinar as engaging and interactive as possible. So we also want to hear from you. And right now, if you enter Slido, you will be able to see the first question there. And I see some people are replying already. Thank you. The question is, which are your main application domains for GPP and NPP products? And now we can go to the next slide. And again, in a second, I will share with you the link on the chat so that you can continue accessing Slido. And lastly, on my side, I just wanted to remind you that this is the second edition in a series of actually 5 webinars. We already had one on drought impact assessment on the 15th of November, which if you missed it, you will be able to see it online as we will be posting the recording. Today, we have the webinar focusing on biomass carbon fluxes, and in January, we will have a webinar focusing on agriculture, in February, one focusing on biodiversity, and in March, one focusing on urban green. Since you're already joining us today, you probably already signed up for other webinars, but if you haven't, you can go to the same link that you used to register for this event, and you can register for the others, and you can, of course, share it with any other people you think may be interested in this webinar or the upcoming ones. And as I mentioned, for the drought impact assessment, all webinars will be recorded and shared online. So if you missed it, you can always watch it later. And now I give the floor to Ludwig.
Thank you very much. I hope you hear me. Okay, so as we start all of these webinars, we start with a bit of a short introduction to the HR-VPP product. So if you've joined the webinar in the past, the drought impact assessments, you will be very familiar with what I'm about to say here. But for all newcomers, I think it's valuable information. So the HR-VPP, the Vegetation, Phenology and Productivity, is something that you will find on the Copernicus Land Monitoring portal under the biogeophysical parameters, and then further within the vegetation category. And this is where we find the HR-VPP levels of products, which I will describe in the next slide. The HR-VPP is a systematic monitoring for the whole of Europe. So what we call the EA 38 plus UK, so that's 38 countries. So including Turkey and non-EU countries as well. And so if we start with defining a bit what is phenology and productivity, they're usually defined as, so first, phenology, the timing of development of the photosynthetically active leaf foliage, which is a bit of a tongue twister. It is simply it's visible as stages of leaf development, so the bud setting, the leaf growth, the leaf shedding, and so on. And it relates to the internal plant processes and is affected by external factors such as light, temperature, and so on. While productivity, and this is of course the main topic of today, is the accumulation of vegetation biomass. It's denoted plant growth primarily, and it's often measured as gross or net primary productivity, GPP, NPP. We will get into this quite a bit today. And it's affected by the vegetation vigor and health. So the product suite in a brief way, it starts with the Sentinel-2 satellite scenes, which where we use the level 1C products. We perform the atmospheric correction within the production, at least in this phase of HR-VPP, where we want a similar atmospheric correction for the whole archive. And from there, we produce vegetation indices, 4 to be exact. The NDVI, I think you're familiar with, the fAPAR, the fraction of absorbed photosynthetically active radiation. We also produce leaf area index, and the PPI, the plant phenology index, which is the main vegetation index later for the production of the high level VPP products. And these are produced on a daily basis. So as soon as the Sentinel-2 scene is made available from ESA, we produce these 4 vegetation indices and aim to deliver them to users within 12 hours from sensing time. And then, so the first level of the VPP production, or the second level, let's say, is the seasonal trajectories of the plant phenology index, and these are produced on a 10 daily frequency by applying a season function fitting and gap filling, which means that we produce full European extent every 10 days. So we have a measurement every 10 days. Without gaps or cloud cover or anything like that. Then further, these seasonal trajectories are used to annually produce the phenological and productivity parameters. I will get into the details on these later. There are 13 parameters for 2 seasons for a vegetation season, or 2 vegetation seasons. And both the seasonal trajectories and VPP parameters are produced annually and made available annually. But the frequency is different, of course, if you follow that logic. Then just to explain a bit on, we use a lot of reference data for a production like this, both in terms of calibration in the ramp up of the production and for validation purposes annually. And here we use data sets such as GPP from eddy covariance flux towers. We use pheno cameras, which is normal cameras taking pictures frequently over certain vegetation. We also use the PEP 725 network of manual field observations. And for some countries, also agricultural crop data is used. And then back to the vegetation indices, just want to visualize here on the choice of a PPI, which we had a significant assessment done in the ramp up of the project, where we selected the PPI due to its showed to be the most sensitive for phenological stages of different land covers. So these graphs were assessed and were taken out for different land covers. And as you can quite clearly see here, you have more of the seasonality expressed from the PPI. But of course, a VPP kind of data set can be produced from all of these 4. But for us, the PPI will show the most fit for purpose. Seasonal trajectories, to visualize a bit on the function fitting and so on. We have the raw vegetation indices here in black points. This is the daily or the 5 daily measurements we have for the same area. We have a Sentinel-2 observation. And in the yellow points, you can see the 10 daily aggregates, which then are fitted to a function that is determined when we can look back at the full vegetation season and get the most accurate function to represent it. And from these, then we can interpolate in between these seasonal trajectories to determine on where we have the season start, the peak of season, the end of season, and so on, as you can see in the green arrows here. And we have, of course, that's the parameters where we have more parameters, which I will get into the next slide. Or no, the slide after that. I just want to visualize a bit on the seasonal trajectories. These can, of course, be used for many applications. Here we can see the impact of drought, for example, in southern Sweden, in the case of the reference year of 2018. When we come back to it again, you see here in blue colors, the vegetation is, of course, not that active. When we reach the summer, we see in July a quite significant drop-off in the values for 2018 on these agricultural fields, which of course has a major impact on the productivity of the season and so on. So it's an interesting use case. So finally, the phenological metrics, or the parameters, as we also call them. We have the, as I've described, the start of season, dates and values. We have the peak of season. We can also then derive the length of season, and values for the slope and for the green up and green down periods of the vegetation season, and also the productivity parameters as the seasonal productivity and the total productivity, which are derived as an integral of this function, right? So if you look in the lower left here, you see the yellow and the blue, kind of the integral under the curve where we calculate the productivity as it is currently in the product. Then further on the lower right, you see some statistics derived from productivity of different land cover classes, so combination with other land cover data sets to get a season productivity and where you have the most productivity in which land cover classes and so on. So yeah. Further, the HR-VPP is very well documented. We have different levels of documentation. So the first one being the product user manual, kind of explaining in a certain depth of the product. And here we have two, one for the vegetation indices and also for the seasonal trajectories and parameters derived with TimeSat. By the way, I forgot to mention the main algorithm here. Then for users who want even deeper knowledge in how the production is set up, we have the algorithm theoretical basis document, where it's in great detail described on the calibration and so on that is set up for this production. We also publish validation reports. So first for the baseline production of 17 to 2020, and then we have annual validation reports for every reference year we add to this production. Then further, there's many different ways to access HR-VPP. Of course, we have the easy access with KO download zip files and so on, but there's also machine-to-machine APIs to enable a more complex way of accessing the data sets, because it is a complex product with a lot of data and the time series and so on. So in some sense, it's also there's a need to have a bit of a refined accessibility. We also publish a set of tools and so on to be used, and we continuously expand the number of tools and that users can use to access the data set in certain ways. And just to mention a bit on the future prospects, we are, of course, aiming for a continued production of this data set. It will continue for many years to come. We also, very relevant for this webinar, we are in our intention is to include a kind of pre-process to users above ground biomass productivity, where we would introduce then the GPP and potentially the net primary productivity as well, straight from production. And this might also mean quite a bit of change in how we do the seasonal trajectories, and the VPP metrics might be based on the GPP estimates and so forth. We also foresee a reprocessing of HR-VPP to align with the Sentinel-2 Collection 1 reprocessing, which you might be aware of, that the full archive is currently being reprocessed, and they are fixing things within the time series, which is very important for a time series product such as HR-VPP. Geometrical stability and so on has a great impact on such a product. And further, we also foresee to limit the number of vegetation indices that are produced and more streamline it to what is actually used for the HR-VPP. But it might change quite a bit on the vegetation indices and so on to be able to fit the above ground biomass production. We don't know yet, but might be some changes coming. And with that, I want to say thank you. There should be a new question on Slido published. So if you want to go back there and answer that, and as Sophia said before, the link is in the chat if you've closed down the site again. And with that, I want to leave the floor to Roel. I'll just stop my share here. There we go. Stop my share so Roel can join. Roel is working for Vito within the production of HR-VPP. And here he's also written a use case, which you can already access, a white paper on how to use HR-VPP for deriving, doing kind of biomass, above ground biomass estimations using the HR-VPP portfolio. And here we will now describe how that's done and what results can be expected from such analysis. Over to you, Roel.
Okay, thanks a lot, Ludwig, for the introduction and also for accommodating this webinar. Just asking for a confirmation if you can share, if you can see my presentation now.
Yes.
Okay, that's good. So Ludwig already introduced the HR-VPP project, and it's basically on top of that project that we have exploited this data to quantify biomass carbon fluxes. So this was a use case in the framework of HR-VPP, where the aim was to demonstrate how we could use the HR-VPP data to calculate products like GPP and biomass production. Now, the major incentive of this use case was basically that there is an increasing demand in Earth observation products that can support carbon budgeting. And to date, no high-resolution GPP and NPP data is publicly available over Europe. The current Copernicus Global Land Service is providing already GPP and NPP, but only at a medium resolution on Sentinel-3. So there is currently a bit of a gap in terms of publicly available data on these variables. And the interesting thing here is that HR-VPP basically provides already the building blocks to calculate these variables, such as fAPAR and seasonality. So the objective of this work was, first of all, demonstrating how we could transfer an operational existing GPP NPP model, which has proven to work fairly well at large scales, to the HR-VPP data. And then we were also prototyping the GPP NPP product workflow from a technical point of view, and we would have an evaluation of the products both at site level and also at some larger scales. So first, a quick recap on primary production. Ludwig already introduced these terms, but for those of you who are not aware what primary production is, just a quick recap. So basically what we want to learn is how much atmospheric CO2 is converted into biomass. And that's basically the definition of primary production. So it's a carbon flux from the atmosphere to the plants who are using it in their biomass growth factories, let's say. So the unit itself is expressed as carbon, or can also be expressed as dry matter or biomass. And typically it's per unit area and also per unit time interval. And the most default unit is gram carbon per square meter per day. So primary production can be split up into gross primary production, which is basically the same as photosynthesis, but then just expressed at large scale and also quantified. So it's the carbon flux coming from the atmosphere into the vegetation. But this is, of course, only the, let's say, the positive side of the balance. Not all of this carbon can be used for biomass production. So there is also losses of carbon. And the most important loss is through autotrophic respiration, which plants need to produce energy for maintenance and growth. And then the second most well-known term in primary production is net primary production, which is basically gross primary production minus the autotrophic respiration. So these are the two typical variables if we talk about primary production, but we must make the story a bit more complete. Net primary production is often also assumed as biomass production, But in theory, there are some additional losses of carbon through the roots, for example, or through volatile organic compounds. So these are additional carbon losses which a plant invests, for example, in nutrient uptake. And if we also subtract these losses from, let's say, the growth, the photosynthesis, then we have biomass production. And then the above ground part of biomass production is something which we call then ABP, or above ground biomass production. So this is basically the full story of the different carbon fluxes which are typically derived from related to primary satellite-based primary production modeling. Now, in this use case, we have worked with an operational algorithm. As I mentioned before, the current global lens Copernicus service is producing already GPP and NPP, but only on Sentinel-3. But we've used a similar, the same algorithm, let's say, to test it in this use case on the high-resolution HR-VPP data. So this is a slide which is a general overview of the model. So it's a typical light use efficiency model, which has three major components. To calculate GPP, you would need PAR, which is the photosynthetic active radiation. And this is estimate of PAR can be done via incoming solar radiation. So that's, let's say, all the energy which enters into the ecosystem. And then we have the observations, how much of this light is actually intercepted by vegetation. And this is the definition of fAPAR. And fAPAR comes here from HR-VPP. So each Sentinel-2 scene, as Ludwig already introduced, is being transferred to fAPAR values for that particular scene. And then we have the modeling component. So that's the component on the right, which is the light use efficiency. And these are basically additional constraints in terms of the efficiency to convert the solar radiation into biomass growth. And typical model drivers are here meteo-based. For example, in our model, we are using air temperature and atmospheric CO2 concentration. The meteo data which we have used here was coming from AG-ERA5, which is an interesting publicly available data set tuned for land monitoring applications. So the analysis was done at two different levels. The first step, we always work at site level. And the interesting in Europe is that we have the ICOS sites. And then in step 2, we upscale the processing towards a larger area. In this particular case, we have done a demonstration over a site in Belgium. So I already introduced ICOS, but just a few words on this. So GPP measurements itself are derived from eddy covariance towers, which are spread all over the globe, although the density of these towers really depends on the region. And in Europe, the different eddy covariance measurements are centralized and organized through the ICOS initiative. So this is a program which is collecting all the data from these towers and then redistributes them in a harmonized and normalized format, which is an interesting starting point for the calculations. And on the left, you can just see two of these towers, one in a forest site in Belgium and the other one on an agricultural parcel. So they are a bit spread over the different biomes. So for this work, we had about 50 sites with data between 2018 and 2021. So first step, site level analysis. As I mentioned before, we are working here on HR-VPP fAPAR, but these data, as I mentioned before, is calculated per scene, and there is no standard gap filling done. So one of the first steps is to do a gap filling and a smoothing of the per scene available fAPARs into a time series. And for this, we have used also the timestat software, which was calculated in HR-VPP to calculate the seasonal trajectories. So generally, we have a fairly good fit. We also recognize that there might be some tuning needed to fit the data even a bit better, specifically to follow the data points a bit more exact, but that's all possible. And here are some validation results. So these are already the scatter plots where the GPP model was applied on HR-VPP and on these AG ERA 5 meteor data. It's being calculated on different time intervals, for example, weekly, monthly, and yearly. And then we have done a validation over these 50 sites from which we had actual measurements over the period 2018 until 2021. So you can see, and that's quite typically in satellite-based GPP validations with eddy covariance measurements, that the line of fit is fairly well, but there's also a large scatter, and there are various reasons for that. I will not describe them here in detail, but it's perhaps something we can further discuss in the discussion rounds. But two examples. So the first one is on a cropland site, and here on the graph you can see three different lines. The green line is the smoothed and gap-filled Sentinel-2 fAPAR, so it has a clear seasonality. Then the red line is the in situ GPP coming from these towers I've just mentioned, and the black line is the Sentinel-2 GPP derived with the TMP model. And here, this is an illustration over a cropland site in Belgium, and it already shows that there is a big difference between the greenness of the land surface and the actual photosynthesis. As you can see, for example, here in this middle season, you can see that the fAPAR actually has very large and extensive growing season because it's green, but we are also in the winter time here, and photosynthesis is actually pretty low. So that's why we need a model to transfer this green line, so the greenness observation, to the actual photosynthesis carbon fluxes, which is then the black line. So that's the first major observation. Then also we still see that specifically for cropland, there can be still some mismatches in the in situ data and the satellite-based GPP seasonality and amplitude. This also has various reasons. It can be, for example, the Sentinel-2 fAPAR gap filling, which is not fully grasping, let's say, the detailed seasonality, but also the uncertainties on the in situ GPP might be one of the additional sources of uncertainty. Also, the model assumptions which we have used here is one assumption for the entire of Europe. I think if we go a bit more into detail and we also have this information, that we can do some specific tuning for cropland at least. For example, differentiating between C3 and C4, and also adjusting the light use efficiency values can be fine-tuned. So this work also triggered us to start up some additional research work, and we're currently having an Horizon project, which is called EvoLand, in which we are targeting these improvements specifically for cropland and grassland. So this is work in progress. Here you can see a similar graph, but then for a forest site in Czechia. So again, the green line is the greenness observed from HR-VPP, but then smoothed and gap-filled. The red line is the in situ GPP from in the towers, and the black line is again the modeled GPP from Sentinel-2. So here you can see, and it's also quite typically in Europe, that our model was able to capture the forest GPP pretty well. Although one of the main constraints still in the modeling is that sometimes drought effects are underestimated. Like if you can see here, here we had a drought event in 2018, and it's not fully captured by the model. Also, to accommodate for this, we're also planning to, are also working on this in the Evoland project to include the drought stress factor into the GPP model. And then some examples at a bit larger scale. So we've used this algorithm that was fine-tuned on the specific ICOS sites that we've done some processing over larger areas. And here you can just see an animation on a 10 daily time interval for a region in Belgium. So now we are already entering summer, and you can see that the GPP values, they go up to 10 to 12 gram carbon per square meter per day. And now we are again entering autumn, so the photosynthesis is lower. And as we are going into the winter, then you see that photosynthesis basically drops to 0 because it's simply too cold. And then again, when spring is emerging, you can see that the GPP values are rising. Why these images also differ a bit from time interval to time interval is because the weather conditions within that 10 days determine a lot about the model performance, not the model performance, but the model outcome. For example, if it was exceptionally cold, or if there were a lot of clouds, then also GPP is constrained for that particular period. So that were the GPP time series. And then again, highlighting the discussion about what should be the target variable. So the most well-known is converting GPP into net primary production by subtracting the autotrophic respiration. Most applications, however, would need biomass production, so the actual biomass growth. But most in situ data, although it's still very, very few and sparse, is mostly above ground biomass production. But most applications and projects, you see that NPP and biomass production, they are treated similar. So the next step is what we have done here as a kind of a demonstrator, how you could use these GPP time series to quantify seasonal biomass production. So we combined them with the HR-VPP phenology. So from HR-VPP, we can extract the start and end of season for each pixel. And we have a time series of GPP for each pixel. And then we can do simple aggregation over time. Then we have the seasonal gross primary production. And in this test, we have done a simple conversion of this aggregated GPP into seasonal biomass production by applying a biomass production efficiency factor. But there are some more complex methodologies available as well, but they also would need some more ancillary data, and ideally in situ data to drive the biomass production efficiency. So here is an example of the seasonal biomass production. So it's again expressed as gram carbon per square meter, but now we are talking about a season. And this is an extract for an urban site in Belgium. So you can see the city, the university city of Leuven, with their surroundings. And you can, of course, clearly see that the forest patches, they have the highest seasonal biomass production, that the agricultural landscape in between is a kind of a mosaic of different productivity levels, and that the urban site in Leuven itself has the lowest production over that season. It is also possible to calculate it for a second season, and the second season would then mainly cover only the cropland sites which have 2 seasons. So to conclude and to think a bit further on this, HR-VPP provides the building blocks for GPP and NPP or biomass production modeling. That's for sure. In this test, we've had reasonable accuracies over the available ICOS sites. We also know which are the elements which we still can improve and which are being progressed, let's say. So gap filling and smoothing is one of the elements. Then also the model evaluation for specific biomes and events, cropland and drought is really important. And also the GPP, for GPP, we have quite a few data points, but for biomass production or NPP, there are very few data points. So that's one of the challenges. I already mentioned that we're working on model updates. And then my last point would be also looking into the other upcoming HRL VLCC products. So this is another high resolution service which will provide maps of cropland, grassland, and forests. And it will the data will be released somewhere next year. And for example, some interesting combinations can be done if we have HR-VPP, then such kind of a modeling approach, and then also these upcoming products. Like for example, if we would have the crop type over Europe, then we can also build a model on top of the C3 and for the C4 crops, and that would allow us to increase the accuracy for the C4 crops. If we have a very detailed crop emergence and harvest, which is also one of the upcoming products, then we can aggregate the main season from the secondary crop season. And I think with this type of information, we go more towards the questions coming from the policy or the industry, especially for agriculture. And some additional interesting analysis, like working with the grassland mowing events and other interesting upcoming data can be done as well. So I'm really looking forward to having all these different products, and then it will be quite interesting. So that was my last slide. I will stop here. I don't know who will take over. It's again.
Thank you very much, Roel. And yeah, we questions we say for the Q&A. We are a bit behind schedule, so hopefully you can stay for another 5 minutes, so we can have the Q&A session as well. And have time for your questions and things you wonder about the product. I want to inform you as well that the third and last question has been posted in the poll on Slido, so please and go in there again and answer. And also now we want to hand over to Jonas Ade, who is from Lund University, who will present on the Ramona project, which is setting up similar to HR-VPP, using TimeSet for rangeland monitoring in Africa. And as well here in high resolution as a continental wide production. So please, Jonas, go ahead.
Thank you, Ludwig. Can you all see the presentation?
Yep.
Fine. My name is Jonas, and I'm from the Department of Physical Geography and Ecosystem Science at Lund University, and we'll mention briefly today about something called Ramona. Ramona is a ESA-supported project called Rangeland Monitoring for Africa using Earth Observation Continental Demonstrator. It's coordinated from Aarhus University in Denmark, and in addition to us as participants, we cooperate with DHI in Denmark and GeoVil from Austria. Shortly about rangelands. They are important livelihoods for hundreds of millions of people globally, and a lot of people in Africa as well. They provide livestock-based food, essential proteins, meat and milk, and income for livestock for a lot of people. They also support livelihoods through other resources, edible wild plants and animals, firewood, etc. So they produce a lot of useful ecosystem services for a lot of people and beneficial to communities, the wider African community, and the world at large, including the wildlife industry, etc. And the capacity of the African rangeland to sustain these functions over coming decades is, of course, one of the important factors that makes ESA and others to want to be able to monitor those rangelands through satellite-based observation, as to provide information for suitable management of such resources. This is the approximate extent of rangelands in Africa, excluding the moist tropical forest and some of the deserts areas, but about 17.5 million square kilometers, so a lot of pixels to take care of. Might look like this, or this, or this. This is a flux measurement station, as mentioned by Roel, that we also use for calibration, but they're not so common in Africa, as we don't have any ICOs in Africa, for example. So there's only very few, less than 10 sites in Africa running these kind of eddy covariance flux measurements. In many areas, we have quite significant seasonality between the dry and the wet season. This is the same tree at these two pictures, so we can have very large differences and short vegetation periods, especially in the Sahel area and some of the semi-arid regions of Africa. There will be animals grazing these resources, not only on the ground, but browsing trees, etc., as well, trying to take advantage of available resources. So in short, Ramona is a 2-year ESA projects for partners. We're supposed to provide 3 core products. That would be the rangeland type, the rangeland extent, and the rangeland herbaceous biomass. And this is supposed to be on 10-meter spatial resolution, and the biomass is supposed to be monthly, so that will be a time series of that, but for a limited period. We're also providing 3 experimental products called biomass anomalies, and rangeland performance, and near real-time phenology. These will be about 300 meters spatial resolution. We provide a lot of these flow chart with arrows and boxes, etc., but we don't want to show them because they're slightly confusing. So we'll look at a simplified project flow here, where we use different types of Sentinel data as input. We use Sentinel-1, Sentinel-1 and 2 in combination, Sentinel-2 and 3 in combination, and we feed those into TimeSat for smoothing and time series analysis. The TimeSat data then feeds into these different products in different ways, where we have a certain numbers of tiles and sites for calibration and validation. And this is the stage that we are in now, where we try to calibrate and validate the products that we are working with and refining them. And the final stage, we were supposed to produce this on 10-meter resolution for the entire continent. So herbaceous biomass. Some parts here will be a little bit redundant to what Roel said, so I will keep that a little bit short. But the herbaceous plants are vascular plants that have no persistent woody stems above the ground. It might be grasses and different types of herbs. That could be perennial plants as well annual or biannual plants. And biomass we talked about before, and production, vegetation production, we talked about before. Biomass is hence the accumulated NPP for a day, for a week, for a month, or for any period of time. In terms of remote sensing, GPP is fairly okay to estimate by remote sensing, but the respiratory losses are somewhat more difficult. This is in the front. We have some herbaceous biomass, but of course we have woody biomass as well in Africa, and these provide essential ecosystem properties as well in terms of shade, capturing aerosols, etc., that actually fertilizing savanna areas and things like that. We perform some in situ measurements where we try to estimate the amount of biomass to use for validation with such a tool called a disk pasture meter that we utilize. If we'll try to go from the sentinels to GPP, we use a similar approach as Roel with a simple light use efficiency model. And we tried and evaluated a few of them, and they look quite similar, where the gross primary production is a function of the incoming PAR and the fraction of the absorbed PAR in combination with the light use efficiency. We then have some restrictions or scalars that limit productivity in terms of temperature or water availability. And those models could be formulated in slightly different ways. The water scalar, for example, could be water pressure, vapor pressure deficit, or soil moisture, or slightly different things as well. For each of these different terms, we also might have different input data. So we might have the incoming PAR from ERA 5, for example, or from MODIS. For fAPAR, we might use an fAPAR product or derivation from NDVI, EVI, etc. So there are some choices to be made for all of those variables here. And for Africa, and in this project, we have some 6-7 eddy covariance sites for calibration. And that's all for 18 million square kilometers. So we would like some more. And this will be an example of how the input and output data for such a model can look. And here we have the gross primary production in grams carbons per square meter of day. Here we have the incoming PAR. We have the fAPAR, we see this is a site in the Sahel, so we have quite low fAPAR during the dry season, then a distinct peak. We have a constant light use efficiency. We have almost no impact from temperature. You see the straight line at value 1, but we have a strong influence by the water availability, and that's true for quite many areas in Africa. And this is an example where we compare it versus the flux measurements. This is from a site in Senegal where we perform flux measurements, and in this case is the mode 17 algorithm, and in this case, we have a light use efficiency of 1, and here we have a light use efficiency of 1.5. So that tilts the line a little bit and changes the relationship. If we then have GPP derived, how do we come to biomass? Well, first thing we ask is, where does it end up? The assimilated gross primary production? Will it be below or above ground? And this could vary, of course, with plant type and place, etc. And how much of the GPP is lost due to respiration, and how much is lost to biomass turnover? So we'll start on the above and below ground. There's a lot of job to dig it out to actually quantify how much of different plants are available above or below ground. So there's not so much data on that from Africa if you look in plant trait databases, etc. We have done some estimates, and there are some literature estimates on that we are trying to use as good as possible. And this graph will show the root-shoot ratio and the corresponding above ground fraction. And in our case, we used a value of 1.9 that was derived from literature. And that means that we have more biomass below ground than above ground. If we have a root-shoot ratio of 1, that means the same amount above and below ground. We, of course, have a above ground fraction of 0.5 and a below ground fraction of 0.5. This is some assumptions that we have to do to be able to quantify the above ground biomass, which is the parts that could be grazed by the animals. Then we have to try to estimate the respiration, and this is also tricky. This is a paper of a colleague of mine where we try to estimate the ecosystem respiration. This is a combined autotroph and heterotrophic respiration and how it relates to factors like GPP, soil water content, and land surface temperature. But this is not singling it out the autotrophic respiration, and that might be quite difficult. So what we've done in this project, that we use something called the carbon use efficiency, and that's the NPP divided with the GPP, and we derived that from a set of global vegetation models. And this graph shows how this will vary over time, and as a seasonality, it varies between 0.48 and 0.6 for each year. This graph shows the spatial variability, shows that the carbon use efficiency is higher when you go further to lower latitudes, 10 degrees here, and it decreases when you go to higher latitudes. And this is a map where this shows the carbon use efficiency for the Sahel region. Some models use just a value of 0.5 for this, and to be honest, I don't think one alternative is much better than the other one. In this case, we used mean carbon use efficiency from an ensemble of vegetation models, I think 12 or 13 different models, and we calculated the carbon use efficiency for each pixel for each month on an average for about 20 years. And you can see the distribution here, average about 0.45, and most of the values between 0.35 and 55. We go to biomass turnover. This is the gradual dying and regrowth of fine roots and other small plant tissues, and you can also calculate the root exudates, etc., that was mentioned by Roel. So if you have a root that grows out on a Friday, and then it dies the next Friday, and the third Friday you go and measure it, then you don't get it in there. So you'll have a kind of biomass turnover that you need to account for. And this have been estimated by some studies, and they show that not accounting for biomass turnovers is actually a factor of 2 to 5 times higher when you account for the turnover. So this is something we have to account for as well. It's very hard to get data on it, difficult to measure, but it's somewhat existing in there as well. So going from sentinels to biomass, we have to take account of the remote sensing part we mentioned before, but also the carbon use efficiency, the above ground fraction, the carbon content, and the biomass turnover. So putting this together and evaluating it, it might look like things like this. And I think we saw this one before, right? So we'll skip that. So the data coming in that we use for this will have affiliated with some uncertainties. This is a graph of the GPP in grams carbon per square meter a day, and for the time series on x-axis, assuming the 100% PAR from the era 5. We decrease this with 10%, we of course decrease the corresponding GPP, and if we increase that, we will increase the GPP. This could be like a ballpark estimate of the uncertainty of the incoming PAR. We accumulate that uncertainty over the year, we'll see that it turns out that assuming 90% of incoming PAR, we end up a little bit more than 500 grams. But if we have 110, we arrive at 620 or something. Well, a difference about 115 grams of accumulated GPP for a year. And this is about almost 20%. So this is substantial uncertainty just due to one factor. We will have uncertainties for a lot of other factors as well. If we're looking at those parameters for the biomass turnover and the carbon use efficiency and the above ground fraction that we also need to put in here somewhere, we have two, we might call these extreme option here to show the differences. But the lower line here, we assume above ground fraction of 0.32 and a carbon use efficiency of 0.5 and a biomass turnover of 2. And here we have slightly different values with no biomass turnover at all, a higher carbon use efficiency, and higher above ground fraction. And here we have a difference of more than 200 grams. This will be quite substantial if you're going to bring your animals into an area and you assume you have 100 grams or 350 grams per square meter. So scaling this up to a sentinel tile, this is an example from Senegal, and the data is from June 2022. This will be the map with lighter areas will have a higher biomass and darker areas lower. This is in the dry season, so the areas that are not close to water or irrigated have very low biomass accumulation, and this will be the distribution. And 1,000 here would mean 10 grams per square meter, so it's not much. We'll go to September. This is peak season. We'll have biomass more or less all over the area and a distribution that looks like that, with a mean value of something 30 or 40 grams of biomass produced per month, up to 80 grams. And this is a gram dry weight then. And we should remember then we'll need to put these uncertainties we looked into before at every pixel here to be able to estimate some of kind of these uncertainties. And that will kind of point out the uncertainties you need to consider when using such data for planning. Going to December the same year, we can see now that we have almost no biomass production here, but these are irrigated areas that could be growing all year around, because here's temperatures and sun is enough, but not water availability. These is irrigated areas. So we apply this for different areas in South Africa, Kenya, Senegal, and Sudan, and we currently work on the validation of the data. And this might look like the graph down here, where we show the field measured versus the estimated on satellite. It should be mentioned that this is not from the Ramona project. This is older data, but that's not super easy to collect and use data sets that are collected with different methodologies. So the black dots here is collected with one methodology in Sudan, and the blue ones is another data set. So they might differ, making these things more tricky. We also might need to consider how the accumulation over time influence this. If we want to accumulate and assume that we have the biomass at the end of the month is a function of 1 day or 1 week or 1 month or 2 months, etc., is something we need to consider, as well as the grazing. We don't have any control if there been a camel eating up all the grass in the pixel the day before or the day after we have a satellite measurement. Now, this is just a tool we use for in the field for these measurements. So then we'll try to upscale this, and this graph shows the tree distribution, because as we're only assessing herbaceous biomass, we scale it with a tree cover from Martin Brandt and company, who made a 3-cover data set for all of Africa. So if there's a lot of trees, we downscale the amount of herbaceous biomass with a linear inverse function as well for these areas. And we try to estimate the herbaceous range of biomass for each tile for the continent. We still have some problems with systematic differences among tiles, but these are things that we're currently addressing within the project. So Lars, it's just a colleague of mine, he also asked me to show just one slide about the phenology, because we're also estimating phenology for these tiles, as mentioned by Ludwig before. So we estimate the length of the season, the start of the season, the end of the season, the amplitude, and the total productivity in a similar way as the HR-VPP product for Europe, and maybe it could migrate to Africa as well down the line. And this one was skips, and thank you.
Thank you very much, Jonas. Very interesting to see how this you apply it in African rangelands as well. And of course, it really showcases the complexity of the modeling and how place-specific it is to perform such estimates. Now, sorry for being a bit late. We, of course, want to facilitate the Q&A as well. Hopefully, you can stay for another couple of minutes. We've received a couple of questions on the Slido. So we can go through them first, and please don't be, please activate your camera or mic and pose a question directly to us, or in the chat is also available. So first, we got a question from someone on, so saying, I'm curious which methodology does the mentioned time set apply in gap filling of the seasonal trajectories? And this is performed with a double logistic function fitting, least squares method, which is calibrated to derive 2 seasons of function fitting. So it's fitting it into a 2-season logic. And this can, of course, be parameterized times that has different methodologies to apply, and also to parameterize them to fit the application. In HR-VPP, we are fitting it to 2 seasons as a kind of to fit it to different type of land cover types, because of course it's HR-VPP is measuring all different land cover types in Europe. And then we have a question for Roel. Have you found any particular challenges, issues when combining GPP with phenology data to get the seasonal biomass production?
Thanks, Ludwig. And yeah, good question. I mean, on natural vegetation, the HR-VPP is very clear. In Europe, you mostly have 1 growing season, and the PPI-based time set approach works pretty well to delineate them for natural vegetation. So I think that's pretty straightforward. The only challenge that we observed was in croplands, because in croplands you can have multiple seasons, and depending on which crop type, for example, winter cereals can start already the previous year, and cover crop seasons can also basically surpass the calendar year boundary. And we noticed that particularly for that, it's a bit more tricky to delineate, let's say, an identified HR-VPP season on cropland to a particular target year. But to mitigate that, I think the upcoming HRL VLCC products specifically tuned for cropland will definitely be a nice complementary layer for cropland. So
yeah. Okay, thank you very much. We have another question as well online. How are you planning on going about the validation process? It was posted quite recently, so I don't know if it's for Jonas or if for HR-VPP in general. So as I briefly described in the beginning, for HR-VPP, then it's we are doing validation for the production every year, and we also did it for the baseline production 17 to 20, and these reports are published online. so you can have a look there. We also foresee quite a evolution in how to validate these products in the future. As I mentioned, the future prospects. But it's as I think has been described today for both talks, it's a challenging product to validate because of the nature of the ground truth data. So it's a time series product, which also needs kind of a time series validation. So a frequent observation data to be able to observational reference data to be able to fully validate. But we are working a lot with the in situ component as well within Copernicus. I don't know if you know, but the Copernicus services is supported by an in situ component where we are greatly trying to extend the availability of these type of data. And of course, in a global context, there's even more needed because in Europe we have quite a bit of reference data, but as Jonas also described, in Africa there's less of it, and I know there's similar products being produced or start production on a global basis. So validation is surely an important topic in this context. That was all questions online. I don't know if there's anyone who wants to pose anything. I see we have received from Sebastian where he's analyzed HR-VPP, so and in a published article. So I highly recommend going and looking at that. It's posted in the chat. I've also received the Slido questions. Maybe I can share that and then we end it. So I can share my screen again. Yes, that's correct. And now I lost you guys. Let me see. Okay, I can see you. That doesn't matter. So on the question, oh, this is a bit, sorry. There we go. On the question, which are main application domains for GPP and products, the majority said agronomy and then forestry and biodiversity ecology. That's interesting, and less so for carbon accounting. So many of you are in the agronomy, which is indeed interesting application. And then which biomass production related variable is most suited for your application? Above ground biomass production, which is as Jonas also explained, how to determine what is above ground in the end. It's very okay. Okay, and then which elements of the HR-VPP, GPP, NPP products, a lot of P's there, would be most important for your application? And you say freely open public available data, which it is, so that's great. And spatial resolution. So I guess from that you are interested in high resolution data as it is currently. Okay, very interesting. Is there any reaction from the presenters on these results?
No, I think in general the results are quite intuitive. I think it's especially interesting to see which are the target variables as well.
Yeah.
I think it's also a bit in line with our expectations, but for sure something we should keep in mind for future work.
Yeah. It's interesting as well with agronomy because a major part of why we, for example, fit it to 2 seasons is to be able to capture the agricultural areas and the seasonality of agricultural areas where you have usually more than 1 season, usually 2, but even 3 in Southern Europe. So very interesting to see that there's much interest within that community. All right, I think I'll stop sharing then. And from my side, there's nothing to add. There is a new message. Okay. There's one more question in Slido.
Yes, if you want, I can read it. It says, an exotic question with respect to these concepts. Are there plans to apply these methodologies also for inland waters, which are part of CLMS?
in what way are these methods applied to inland waters? So
I don't know if the person who asked wants
Yeah.
to give more details.
is it Thomas maybe?
Yeah.
Okay.
I'm sorry for this very strange question, maybe, but for sure, inland waters belong to the Copernicus land monitoring services.
Definitely.
Strange enough, but they belong to CLMS. And in inland waters, for sure, primary production and chlorophyll A development during the time of a year are both also very important for assessing the water quality status of an inland water, lake or whatsoever. And for sure, your concepts are applied to agriculture and soil, but it would be very interesting to have these parameters or similar approaches also for the assessment of the primary production in inland waters. And therefore, it's a little bit exotic, I know, but
Yeah,
it
no,
has some reasoning.
It was, I suspected that this was the intention of phytoplankton and so on. Not within HR-VPP, but as I described in the beginning, it's part of what we call the biogeophysical parameters, where we also have currently on the portal is called snow and ice, but it's expanded to water, snow and ice. And I don't know if it's in the near future, but there will be developments in the water, snow and ice production, taking into account more of these parameters as well, water quality and so on, which in a similar way as HR-VPP, it's also doing the near real-time monitoring, heavily time series dependent production. So yes, I cannot say for sure on all the variables you said on what's it called, phytoplankton A monitoring and so on, but I know there's such products coming.
Okay,
Looking at
thank you very much. Thanks.
If you don't mind staying 1 minute longer, we have another question that it's probably for Jonas. How usable is the African case compared to other parts of the world? Can the method experience be used with some modifications?
Be used in other areas?
Yes.
Well, this is one of the key problems with remote sensing methodology. Even if you get strong local correspondence between your in situ data and your estimate, they're not always possible to move them and have simple algorithms that is applicable at different vegetation types. And as we might need to stratify, as was mentioned before, among C4 plants, C3 plants, we might have different relationships in different climatic zones and things like that. So it's not straightforward to extrapolate or move these, but there are methods, for example, or light use efficiency methodologies that are global. For example, the mode 17 that uses biome specific parameters for the scalars and for the light use efficiency, etc. This is one way to go about to make these kind of functions or calculations more transferable to other biomes and other environments. But it's not really straightforward, and preferably you want a bunch of flux towers or useful both calibration and validation in each of these regions or plant functional types, or what you want to call this.
Thank you very much, Jonas. I think that was the last question for the day. Sorry again for dragging over time here, and thanks for you who could stay. And we will, of course, want to facilitate the Q&A within the 1 hour as well, because some people have to leave for other meetings and so on. So thank you again. Yeah, that was from Roel to Thomas. Okay, so we have a hand raised. Do you want to pose your question, Havid?
Hi. Am I audible?
Yep.
Yeah, this is Javed from India.
Okay.
I have a question to Jonas that how much it is important for the modeling that the ground to data. We have the large variability and the heterogeneity in terms of, if you see the forest ecosystems here, particularly in the Western Ghats, and how difficult it is, to predict with such type of the model when there is a large heterogeneity in terms of the structural way as well as in terms of the, the diversity wise as well.
Well, I had somewhat problem to hear the question here, but if I got it corrected, there was something about the field data quality, right?
Yeah, I'm saying, how important it is for such type of the modeling that the ground data plays an important role, right? When particularly in the ecosystems where we have the large, the heterogeneity of the, particularly the diversity heterogeneity.
Yeah.
We have the Western Ghats here. Then how difficult it is, such type of models, how they will work in heterogeneous forests.
I think that is extremely important, and many of those, what we say, normal satellite programs that put millions of dollars into space, into receiving stations and satellites, but somewhat less into field data collection. And if you're in a spatial heterogeneous areas, you need a larger sample, and preferably you also want to have separate your calibration from your validation data to make your evaluation independent. On the other hand, is such data collection in the field quite expensive, and we collected square meters here and there in different parts of Africa, but we have millions of square kilometers for estimate. So it's got to be some kind of balance, but there might be options to have your type of crowdsourcing information, people measuring plant height or taking pictures from mobile phones and so on, to get somewhere in between to maybe have less quality but higher quantity of measurements that could be used for validation. But it's an important part of the method development, especially in areas where you're lacking a lot of flux stations like Africa, for example.
Okay, thank you.
Thank you very much. Okay, so now we thank you very much for your interaction as well. And don't forget the rest of the webinars. We have 3 upcoming in January, February, and March, as we explained in the beginning. So please sign up and join us for those as well. Thank you very much.
Thank you.
Thank you. Have a nice day.